Welcome to Physics 550, Solid State Physics. This is Module 8, where we explore superconductivity and modern materials. I am Dr. Moses and Tom's assistant at Tuskegee University. The key outcomes for this video include explaining superconducting phenomena and the Meissner Effect. We will distinguish between Type 1 and Type 2 behaviors and understand the physical intuition behind Cooper pairing. Finally, we will identify the transition from bulk materials to low-dimensional nanostructures. The discovery of a new state of matter occurred in 1911 when Kamerlingh Onnes found that below a critical temperature, the electrical resistance of certain materials drops to exactly zero. This is not just a perfect conductor, it is a thermodynamic phase transition into a macroscopic quantum ground state. Superconductors exhibit perfect diamagnetism, known as the Meissner Effect. Unlike a hypothetical perfect conductor, a superconductor actively expels magnetic flux from its interior, ensuring zero magnetic field inside the bulk material. This proves it is a unique thermodynamic state. We can model a superconductor macroscopically using the London equations. The London penetration depth, represented by lambda, indicates the distance the magnetic field penetrates the surface before decaying exponentially. Surface supercurrents flow within this layer to cancel the bulk field. Superconductivity involves a battle of two length scales, the penetration depth, lambda, and the coherence length, psi. Psi represents the spatial size of the superconducting electron pairs, known as Cooper pairs. The ratio of these two lengths, the Ginzburg-Landau parameter, dictates how the material responds to strong magnetic fields. Superconductors are categorized as Type 1 or Type 2. Type 1 materials, like lead, show complete flux exclusion until a single critical field, Hc, destroys superconductivity. Type 2 materials, such as niobium titanium, feature a mixed state, where magnetic flux partially penetrates via quantized vortices between lower and upper critical fields. The microscopic paradox is that electrons naturally repel one another due to Coulomb forces. Yet in a superconductor, a fluid of mutually repulsive electrons coordinates to flow as a single, frictionless, macroscopic wave. They must somehow find a way to attract. BCS theory offers an explanation through the elastic mattress analogy, involving electron-phonon coupling. The first electron distorts the positive lattice, creating a localized positive charge. A second electron is attracted to this wake, forming a loosely bound Cooper pair that acts as a single unified particle, or boson. The binding of Cooper pairs opens an energy gap, e.g., providing immunity to scattering. To scatter a Cooper pair, which causes resistance, you must break the pair apart. If the thermal energy is smaller than the gap, lattice vibrations do not have enough energy to break the pair, allowing current to flow unhindered.
High-temperature superconductors broke the rules of BCS theory, which suggested a strict theoretical limit for the critical temperature around 30 Kelvin. In 1986, complex copper oxide ceramics achieved superconductivity above the boiling point of liquid nitrogen, 77 Kelvin. The mechanism for these HTS materials remains a major unsolved mystery. Topological materials are a modern frontier conceptually linked to superconductivity. Topological insulators behave as complete insulators in their bulk, but feature highly conductive, protected states exclusively on their surfaces. Electrons in these surface states are quantum mechanically protected from scattering, functioning almost without resistance.
Dimensional confinement explores what happens when a material shrinks below the electron coherence length. The continuous energy bands break apart. Electrons become trapped, transforming classical bulk materials into nanoscale quantum systems, like quantum wells, wires, and dots, with discrete, tunable energy levels. Superconductivity and modern materials have profound applications. Type 2 superconducting wires are used in MRI to generate massive magnetic fields. The Meissner Effect is applied in maglev trains for frictionless transport. Quantum dots provide hyper-precise, tunable wavelengths for medical tagging and QLED displays. This concludes the synthesis of solid-state physics. We've explored lattices, phonons, electron bands, and now superconductivity. You now have the theoretical foundation to understand everything from the silicon in your phone to the superconducting magnets of the future. Congratulations on completing PHY 550.